Welcome to Nano Matters, the podcast that explores examples of nanotechnology. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Here with me today is Adam Rondinoni, Co-Director of the Center for Integrated Nanotechnologies at Los Alamos National Laboratory. So Adam, how will nanotechnology help us with clean energy?
Let me just say thanks for having me on. Super excited to be here today. Now, there are all kinds of great ways where nanotechnology is already impacting clean energy and will continue to impact clean energy. So if we think about, what we're already doing, there are lots of examples, but one of my favorites, of course, is battery technology. There's been an awful lot of research in the realm of nanoscience on improved electrodes and separators and control of structure at the nanoscale and electrodes. And all of this improves battery performance in terms of power and energy density, as well as safety. And so we can look across the clean energy spectrum, solar cells, batteries, electronics, power electronics. I would argue all of this has been improved by the principles of nanotechnology at one point or another. Now, going forward, of course, we're doing all kinds of things where we think nanotechnology will have impact. Solar cells, we think about a photon coming in and striking a semiconductor and creating an electron hole pair. And the efficiency of extracting that electron hole pair is determined largely by the structure at the nanoscale, right? So control of interfaces between P and N semiconductors in order to minimize losses and increase connectivity and such. And we're all working on that. Of course, our group has worked on catalysis for a long time, including control of electrochemical reactions using nanostructures.
I'm looking at an article about some of your past work. And it's talking about taking waste to fuel technologies. So using electrochemical process, like you just mentioned, in taking carbon dioxide and turning it into ethanol. And I also see in this article that your discovery was a bit of an accident. So can you talk about how you take a waste chemical like carbon dioxide and turn it into a useful liquid like ethanol? And then a little bit about the surprise that you had during your experiment.
Sure. So if we think about CO2 or carbon dioxide, most people hear about carbon dioxide because they know we exhale it and we make it, we generate it when we burn things, which means that due to industrialization, it's piling up in the atmosphere and it's a greenhouse gas and it's making the earth warmer. So what we were really thinking about was how do we use nanotechnology to control a complicated reaction, right? And so a complicated chemical reaction might have multiple steps. And so in a lot of chemistry, all the steps kind of happen at once, at least in terms of synthetic chemistry that we do in a laboratory. Nature, on the other hand, is very good at breaking up a complicated reaction into multiple steps and then controlling those steps so that they happen sequentially. So step 1 happens at enzyme A and step 2 happens at enzyme B and that sort of thing. This is an area where we as scientists, we haven't really learned to match what nature is doing. And so we were thinking about using nanotechnology to control complicated reactions. And the reason for that, of course, is with nanotechnology, you can space reactive sites, you can arrange them in such a way and take advantage of physical entrapment and diffusion lengths to try to make sure that step 1 occurs at site A and step 2 occurs at site B, and so on and so forth. And so we were studying a particular type of coated carbon that we plasma coat onto surfaces. We call that carbon nanospike. And we were using it to support copper nanoparticles, which are known to be electrochemically reactive for CO2, at least in the bulk form. Copper is known for this. And so we were just hoping to take CO2 and maybe do an initial reaction. We hadn't actually gotten to the arranged catalyst we were hoping to get to. We were just studying an initial step. And we were thinking might make methane or something simple like that, or methanol. And we ended up detecting, in this case, large amounts of ethanol coming off. And of course, ethanol is a 2-carbon product, right? And so if we look at taking CO2 and converting it to ethanol, you need 2 molecules of CO2, a bunch of water, and 12 electrons. And so something more complicated was going on than we originally anticipated. And then upon further investigation, both experimental and theory work, turns out that we had actually created a sequential catalyst, but we didn't know that we had done it at the time. And it was because the carbon was playing an important role in 2 out of 3 major steps that was unanticipated. So yeah, it was serendipitous. On the other hand, we kind of set out to do what we were trying to do.
So it just didn't happen quite the way you expected it to.
Right. Well, that's good science.
Yep. So if you can take carbon dioxide and turn it into ethanol using this nanocatalyst, is that going to help us deal with global climate change and excess carbon dioxide we have in the environment?
I like to think yes. And of course, I should point out, although we had the highest Faradaic efficiency that had ever been reported, plenty of other groups, really talented people are working on this around the world, right? And so this is something that lots of people are working on because they all understand that as wind power and solar power grows, we're going to have an abundance of clean electrons, and then we can use those electrons to make electrochemical fuels and other chemicals, right, that we're going to need in the future. So the majority of our chemical feedstock today comes from crude oil, right? We drill for crude oil and we don't burn all that crude oil. Believe it or not, we separate it into components like benzene, for example, and then we'll take that and we'll use it to manufacture other things like plastics and pharmaceuticals. And so as we get away from burning crude oil, we're going to need replacements for all these chemical feedstocks. And so while ethanol is interesting, ethanol is definitely not the only target. And it would be really neat if we can make heavier alcohols or other molecules as well. I think electrochemistry, particularly nanotechnology controlled electrochemistry, is actually the pathway for getting there. So making an electrochemical benzene, for example, you can imagine that's a 6-carbon molecule. It's only partially reduced. You need to be some very interesting controls in order to get benzene rather than hexane. And that's a great science question that people could be working on. So I do think that electrochemistry has an important role to play by converting clean electrons from wind and solar into physical chemical products that we need. When we think about fuel, of course, while we all like electric cars, I do too, electric transportation is probably not appropriate for every circumstance, right? And so people who drive to work and their car sits in the garage overnight or at work during the day, that's an ideal situation for an electric car because there's plenty of time to charge. If you think about high duty cycle vehicles like trains and cross country trucks and airplanes, suddenly now energy density and refueling time is very important. And it could very well be that electrochemical fuel would be better in those circumstances because you can refuel very quickly. You can store electrochemical fuel and all you need is a tank. You don't need a fancy battery. And so there are certain advantages in certain circumstances. And I think that electrochemical fuels can definitely fill that role. And of course, some people have range anxiety and things like that. And with a electrochemical fuel that's easy to store and transport and refuel, you really don't have those issues. But you can potentially have the same outcome, which is clean transportation, as you would with an electric car. So I think it's definitely worth pursuing this, and we should be pursuing this. It's complementary to battery transportation.
So it sounds like maybe it's an all of the above approach. And we need to pursue a lot of different avenues of clean energy to tackle this big problem.
I absolutely agree. This is a very large scale problem, and we have a hundreds of year old infrastructure built on fossil carbon fuels that we need to replace. And it's very extensive and it's highly variable. And so there are lots of different things we need to do to replace fossil carbons across the board. And so electrochemistry is definitely a way.
So you mentioned nature and how chemical reactions happen sequentially in nature and that in your experiments you were trying to replicate that. Can you talk about other things that nature teaches us about these electrochemical reactions?
Nature teaches us all kinds of things in terms of chemistry. Nature is very good at compartmentalization, right? And so individual cells and then other structures within cells are, of course, highly compartmentalized. And that compartmentalization can control complex reactions as they proceed from one step to another by providing different reaction environments, controlling feedstocks, and things like that. All of this, of course, is outside the reach of what we can do currently in science. Maybe we can do some of this at the laboratory level. Doing it industrially, of course, is we're just not there yet. So with electrochemistry now, specifically, we tend to think about electrochemistry as just reactions that occur on surfaces. And that's not how nature works, right? And so if we can use nanotechnology to compartmentalize electrochemical reactions, to have different environments where reactions can take place so that we can get that step 1, step 2 type sequential mechanism, I think all of that would be beneficial. And it's only going to be accessible through the principles of nanotechnology and material science at that length scale, because that's the relevant scale.
Just to provide an example, and in nature, when you think about photosynthesis, and we're taught that plants take up carbon dioxide and create oxygen, is that the type of lesson from nature that you're talking about?
Oh, so that's thinking maybe at the systems level. And so if we think about systems level and the role of electrochemistry, this is actually a really interesting question. Your average corn plant is about 1% efficient at converting sunlight to usable energy, to starch. Now we've got solar cells that are 20 to 30% efficient. You can couple that to an electrochemical reaction, which is maybe 30 to 40% efficient. And suddenly what you find is we can actually do better than nature in terms of straight energy efficiency. And we can do it without the need for, say, making large amounts of fertilizer and having farms and things like that. And so I actually think that what we can do technologically is probably going to be better than nature. In terms of making electrochemical fuel, yes, we can potentially harvest energy from the sun or wind, convert it to chemically reduced products in order to make what we need to make, and we'll do it better than nature is doing it, I believe. We're already showing that at the laboratory level. Whether or not it can be scaled to industrial levels, that's something for the entrepreneurs, not the scientists necessarily. But from what I'm seeing, we're going to get there. Companies are doing this.
Wow, that is very exciting. Do you have any closing thoughts that you'd like to share with our listeners?
I'd just like to say thanks to the American public for supporting basic science. We're all here working on your behalf. And of course, I think to be successful with climate change, what we're going to have to do is develop technologies which frankly don't reduce the quality of life, right? People won't accept giving up what they already have. So we just have to figure out how to do it in a way that's cleaner. And I would say the scientists are definitely working on it from that perspective.